Okay, Chapter 4, the easy questions for Chapter 4 of Statistical Rethinking, second edition. The easy questions, we'll get through 3 of 5 here. And none of this actually requires code. It's just conceptual. So the first question is, in the model definition below, which line is the likelihood? And so it wants to know which of these 3 lines is the likelihood. Okay. Well, the likelihood is, if you remember to Bayes' theorem, the likelihood is, well, actually I have it written down here. Where is it? The likelihood is the probability of the data given your hypotheses. And in this form, the hypotheses are the possible values of your parameters of mu and sigma. Okay? So every value of mu and sigma are hypotheses as to what could have generated the data. Okay, and so we see that that it's here. Okay, so the likelihood is saying that y, which is the data, and the little subscript means each individual observation within the data, is distributed by a normal distribution with mean mu and standard deviation sigma. The next 2 lines, notice that we have where we were using mu to define the likelihood. We now have a line for mu, and so this is actually a prior for the value of mu. And then also we have sigma, which also defined the likelihood, and it has a prior of an exponential distribution. Now, the normal distribution has 2 parameters, mu and sigma, and so when we're defining mu, we're saying it is also a normal distribution. We could have defined it, or we could have put a prior with many different types of distributions, but we're saying that the average of mu is 0 and the standard deviation of mu is 10. And so these values are independent of these values here. And similarly, the exponential distribution just has one parameter. It's called lambda usually, and it has and here we're saying lambda equals 1 for our prior. Okay. Next question, in the model definition given above, so here, in the model definition given above, how many parameters are in the posterior distribution? Okay. So the answer to this is that after you run Bayes, you get a posterior distribution for every parameter in the model. So let me back up a little bit. What is a parameter? Well, a parameter is a value that is not contained in the data, that is not observed. Okay, so data is the values you observe, and a parameter is a value that you did not observe and are now trying to estimate. Okay, and so here we have that mu and sigma. We did not observe mu and sigma. We are trying to estimate them based on what we did observe, the data, y. Okay, and so in this case we have we get a posterior for every parameter. So we have 2. Okay, now let me back up, and what I just said is not completely accurate. The truth is that we get a posterior distribution for every parameter that is not itself defined by further parameters. And so that's a weird thing to say if you're not familiar with this. So let me give you an example where we have a posterior without certain parameters that were in the model. Okay, so we have the same model here, or almost the same model, but here we're defining mu in terms of other parameters, alpha and beta, and x is usually denoted part of the observation. Y is the observed outcome, and x is something that is part of the data that we think explains y. Okay, so here we have mu defined in terms of other parameters, alpha and beta. And alpha and beta now have their own prior distributions. And then we have that sigma up here, and the likelihood remains the same. And so even though here we have 1, 2, 3, 4 Greek letters, Greek letters usually denote the parameters. One of our parameters is defined in terms of other parameters. So our posterior distribution will kick out only 3 posteriors. None for mu, because it's defined in terms of other parameters, but 1 for alpha, beta, and sigma. we can reconstruct, we can infer later, and we're not going to this here, but just so you know, we can reconstruct the posterior for mu by using the posteriors we get from alpha and beta. Okay. Okay, so finally, we are supposed to take this model that we saw in the first question and try to write out Bayes' theorem. Okay, so recall that Bayes' theorem, roughly speaking, looks like this. It is the posterior distribution equals the prior or the priors. Notice we have multiple priors here, times the likelihood, and all of that divided by the marginal. Okay, so let's just try to start filling in each of these terms. So, so the first thing is we need a posterior, or we need to know how to write the posterior, and the posterior again is the probability of the hypothesis given the data, and our hypothesis is in terms of the parameters. Which parameter values, what is the probability of the different parameter values given the observed data? That's what our posterior is going to be. And we also need a prior for these parameters. Okay, and so we have a prior for mu and a prior for sigma. Okay, and in this case, we are saying that each of these priors, we are picking them independent of the other parameter. And so when we are multiplying probabilities, prior probabilities in this case, and we don't think that they affect one another, then we can just multiply them straight across. Okay. So we also need one for the likelihood. I feel like my, oh, sorry. So before we get to the likelihood, we're going to expand these terms right here because we already have said that mu, the probability of mu, is distributed as a normal distribution and sigma as an exponential. So we're gonna wriggle that into our notation here. So we're going to rewrite this as this. Okay, mu is a normal distribution with parameters 0 and 10, and sigma is an exponential distribution with parameter 1, lambda 1. Okay. And now for the likelihood, actually I'm going to pause a second and just fix this. Okay, anyway, so we're back. So now we're on to the likelihood. And again, remember the likelihood is the probability of observing that data given the hypotheses, where the hypotheses are given here in terms of the parameters. Okay, and so this is what the likelihood will look like. But we already have, we've already established that we are assuming in our model that the data is distributed normally with parameters mu and sigma. So we're going to expand this to that. Okay, and then finally the marginal. And remember, the marginal is just the likelihood weighted by the priors. Okay, so and we're going to combine all of those. And so when we combine something, we either sum or integrate them. Okay, so we have the integration, and notice we have two integrals because we are combining over both mu and sigma. We have two priors. Okay, and so we have every likelihood, the value of each likelihood multiplied by the priors. Okay, and we're doing this so this just looks like the numerator. Okay, but we're doing this for every value of mu and sigma. All right, that's what our marginal distribution is defined as, and so we can expand that here. Okay, just using the terms that we've already used above. So when we put it all together, our posterior distribution, as we've come to know it, with just kind of the labels for the different terms, in condensed form, looks like this. Okay, so we have our likelihood here, our priors, and our marginal. Okay, and then when we want to expand that out into the distributions that we've already assigned for these different priors, we have again the likelihood multiplied by 1 prior, 2 prior, and then all of that over the integral, the marginal distribution, which is the, I should put d mu d sigma here, but d mu d sigma here, and that's the answer number 3.